Hi, hi everyone. Good morning. Welcome.
Thank you.
Thank you for your participation in this session, in person or in line. This is the session BIO3, Biomedical Engineering, Biomimetics. The first word is of the doctor Paola Rondon Villarreal from Colombia. Identification of novel potential anti-cancer peptides in genoma periplaneta American cockroach using informative tools.
Thank you. Good. ¿Desmentidas? Creo que no. ¿Eres acá? No pasa. Okay. Yes. Okay. Good morning, everyone. Today, I would like to start with some data about cancer around the world. For example, for the year 2022, there were like 20 million of new cases reported around the world, and the bad situation is that it is believed that by the year 2050 there will be around 35 million of new cases, making cancer a really big problem for human health around the world. Another big problem, is that common cancer treatments are not as efficient as we would like to be. For example, they have severe side effects. They have limited selectivity, which means that they attack both cancer cells and normal cells. They develop some drug resistance, and they have a high cost and accessibility issues, especially in our countries. I'm talking from Colombia. It is not easy to have the treatment in the correct time, and it's expensive. So we need new therapeutic alternatives, and we need it now. Therefore, we are working with peptides, which are small molecules that are part of the main immune system of animals, and they are also found across all living organisms. And the important part is that they present multiple biological activities, which means that they have, for example, antibacterial activity, antiviral activity, and in this case, which is our main goal, anti-cancer activity. So let's talk about what is an anti-cancer peptide. These molecules are emerging as the novel promising solution because they are very selective attacking cancer cells. This is huge because they will leave normal cells intact, but they will destroy cancer cells. And they have different mechanisms of action. For example, they can make membrane disruption, apoptosis induction, which is like they are going to induce the death of these cancer cells, immunomodulation, among others. These molecules are so effective that they are already, some of them approved as trial drugs, and they are also some approved by the FDA. In this slide, we can see some of the most popular peptide databases, and these databases contains the information of these molecules that have been tested experimentally. So in these databases, we can find the sequences of these peptides, and we know that they have displayed, for example, antibacterial, antiviral, or anti-cancer activity. Well, they have even more activities. But right now, I'm going to talk about PVA-ASP, which has these statistics that are interesting for us. For example, the peptides that are reported in this database, the 67% of them come from the kingdom Animalia, 18% come from bacteria, 8% from plantae, and 7% from fungi. In the kingdom Animalia, the phylum Arthropoda contains around the 80% of different species. And in this phylum, we can find insects, arachnids, crustaceans, and myriapods, with being insects, the topic of this work, which is quite interesting for us because there's many studies that have found anti-cancer peptides from these insects. For example, they have found peptides from Periplaneta americana, Bombix mori, Pieris rapae, among others. And the problem, I would say, is that they found these peptides by experimental procedures. So that means that they have to collect the insects, they have to put them in different situations, make the synthesis test, and everything that makes the cost and time of discovering these molecules not as effective as we need them. So the proposal of this work is to use bioinformatic tools to reduce the cost and the time associated in the search of these new anti-cancer peptides. How can we do that with bioinformatic tools? By fortune, there are multiple genomes available, and one database that is the NCBI database. This is the link of this database. And for example, for the case of American cockroach, we could obtain the entire genome with this gene bank ID. And the first step is to identify the open reading frames in the genome. I'm going to explain what is that. But once we have this identification, we can find the possible peptides that this insect will be displaying in normal, in the existence. So, for example, in this slide, I'm showing you a small part of the DNA sequence of the chromosome 1 of Periplaneta americana. And the identification of open reading frames is to start analyzing the sequence until you find a start codon, for example, this one, ATG. And after that, you divide the sequence in groups of 3 letters. And each group of 3 letters is known as codon. And this each of one represents or specifies an amino acid, which is molecules that the peptides are confirmed by these amino acids. So each one of these codons traduced to this one of these letters, and the join of them confirms the molecule that we are looking for. In this part is also worth mentioning that by using computational tools, we don't need to do the transformation to DNA to RNA, messenger RNA, and then to protein. We can just go to DNA to proteins, or in this case, peptide, which is a small protein. So with that in mind, the first step was to obtain the entire genome of this insect. Then we use an open source tool that identifies all those open reading frames, which is ORFIPy. They have in their code 3 start codons and 3 stop codons. And with this tool, we could obtain a library, an initial library of around 79 million possible peptides between the length of 5 to 20 amino acids. So if we are going to do experimental tests, we don't need that huge amount of possible peptides. We need to do a virtual screening, and we need to do it as specific as possible because we have limited resources in the experimental part. So the first step was to eliminate the duplicate peptides and eliminate those sequences that have the letter X, which is that the amino acid is ambiguous, so it's not quite sure which amino acid is in reality. And after that, we obtained like only 43 possible million peptides. Then, considering the results in the work of Ian and Ray and collaborators, the rules that were defined was to remove the peptides that do not include lysine, which is the letter K, or arginine, which is the letter R, and also remove those peptides that contain more R letters than lysine, K letters. And after that filter, the library was for around 14 million possible peptides. The next step to reduce this even huge amount of molecules was to select those peptides that contains cysteine, the letter C, in the N terminal, which is the first 3 letters of the word, or isoleucine, which is the letter I, in the C terminal, which is the 3 last letters in the word. Doing that the amount of peptides reduced significantly, and now the new library was for around 4 million possible peptides. Then the strategy was to select those peptides that has physicochemical properties similar to those reported by already proved anti-cancer peptides in the database DBASP, and we established the interval with the values of anti-cancer peptides by removing those, but selecting only the peptides that are in these ranges. The new size of the library was around 3 million peptides. Then artificial intelligence tools are quite remarkable, and there is one that is anti-CP2 tool that is available at GitHub. This is the link where you can access this tool. This tool uses recognition algorithms of pattern recognitions, and they can classify peptides that could display anti-cancer activity to those that could not display this activity. Here we obtained the most significant reduction in the library because the initial library before anti-CP2 tool was around 3 million peptides, and later only 28 were classified as possible anti-cancer peptides, which is a great number to work with. Then there is also a really important property that is the toxicity of the peptides, because we don't want to find toxic peptides. So this tool is also using artificial intelligence techniques, toxin prep-free, and they can detect or they predict the toxicity of the peptides. So when we applied the 28 peptides in this tool, only 2 were predicted as non-toxic. So these are the 2 peptides that in a future work we are going to test experimentally. And the prediction of the possible 3D structure was done with AlphaFold collab, and they display alpha Alice structure, which is like the curly structure that you see in the slide. And this is very typical in anti-cancer peptides. Just to test the screening protocol that we did with the genome of the Planet Americana, this protocol was applied to the list of reported peptides, anti-cancer peptides in this database, DBASP. There were like 2,000 anti-cancer peptides already tested. And after this screening process, which was really strict because we needed only few molecules from that, they select 19. So it's like a really big number in comparison with the genome of the coverage. And just showing some of the structure of the anti-cancer peptides that had already been tested. They are similar in the ring that they have in some of the extremes, and they also display this curly structure. In terms of physicochemical properties, even though that the range of value was quite broad to select the possible peptides, they display similar values in the neighborhood of these anti-cancer peptides. So it is believed that they could display anti-cancer activity in the experimental tests. Therefore, as the conclusions, the protocol developed in this work could be applied to different genomes to create libraries of new potential anti-cancer peptides. The 2 selected peptides from Planet Americana were not found in any of these databases, APD, CAMP, or DBASP database, suggesting that they have not been tested for any biological activity before. So it is interesting to test them in the future work experimentally. And finally, future improvements is to develop new classifiers that help us to reduce the huge number at the beginning, like the 79 million possible peptides. But to do that, we need to create Python packages, so we could use Linux terminal to do this virtual screening. So these are the future work that we are going to be working. And thank you very much. And questions?
Yes, I have a question.
Okay.
Do you know what is the action mechanism of these peptides over the cancer cells?
They have many of them, and to determine the exact mechanism of action, actually, it is quite difficult to do it experimentally. So in the database, you cannot divide them like this is a membrane disruption, this is apoptosis induction. You have to mix them all.
Yeah.
But yeah, definitely it's quite important if we could in the future divide them by the different mechanisms of action.
Thank you.
Thank you. Thank you.
A lot of information. Which could be the informatic tools to identify anti-cancer peptides in the genome, how this works?
Okay, so there are tools. There are actually many tools, but most of them are only a web server that allow the user to upload like 1,000 sequences per time. So it won't be possible to do a filter, a virtual screening of a library of million peptides with those tools. Certainly, scientific community working in bioinformatics are interested in developing new tools, but as I mentioned, it is more important to develop Python packages probably or command line packages that you can use in a script. So if you have millions of molecules, you can do the filtering with those tools. So we are going to develop, but there are some more that they are quite new that we are going to test out.
Any question?
Okay, thank you very much.
The second one is method for adulteration detection of diesel biodiesel full by palm on using permittivity and 2.45 gigahertz with Eden Serafín Hernández Gómez.
Hi, you can see my screen.
Can
Can you hear me?
Yes, we can see.
Okay. So, my name is Eder Serafín Hernández Gómez. It's Eder Serafín Hernández Gómez, and I'm going to present the work called Method for Adulteration Detection of Biodiesel Blend Fuel, E15, by palm oil using permittivity at 2.45 gigahertz. The authors of the work are Eder Serafín Hernández Gómez from Tecnológico Nacional de México Campus Acayucan and José Luis Álvarez Flores from Universidad de Colima. The content is introduction, dielectric properties, methodology, results, conclusions, and references. First, introduction. Well, biodiesel is a biofuel obtained by the transesterification of oil of animals, and that means for testing and materials and the European standard. Biodiesel has become a promising alternative to fossil fuel for these engines due to the environmental consequences of this type of engines and the decrease in oil resources. It is friendly to the environment, low emissions of carbon monoxide and particles. Renewable, highly degradable, it has zero toxicity, and it does not release hydrocarbons. In Mexico, the norm 016 CRE 2016 standard indicates that pure biodiesel must be mixed with petroleum products prior to sale to the public or final use. the B15 diesel biodiesel blend, 15% biodiesel and 80% fossil diesel, is a fuel whose sales have increased significantly in the Mexican market. This mixture is highly subject to adulteration with vegetable oil as a result of incomplete conversion of the oil to ester during processing. In this sense, palm oil is an important vegetable to biofuel production due to its use as a low-cost raw material. Standard method for evaluating the quality of biodiesel and diesel biodiesel blends are time-consuming and require specific high-cost equipment. In addition, they generate emissions and polluting waste. Real-time measurements technique such as infrared spectrometry have been used to determine adulteration of this biofuel, but they present high errors in their measurement results. Even the level of adulteration they consider is slow. The microwave dielectric spectrometry method, in which the permittivity of the material is used to determine its characteristics, provides an opportunity for implementation of rapid, non-destructive measurements that can be performed in situ or only if of this work was to dielectrically characterize several liquid samples with different concentrations of palm oil in B15 diesel biodiesel blend in order to determine the adulteration of the latter. So dielectric properties. Permittivity is a complex quantity whose real part is called dielectric constant and the imaginary part is called loss factor. The dielectric constant indicates the storage of energy due to the polarization of a material in a presence of an electric field. The loss factor indicates the energy dissipation in response to the applied electric field. Methodology to measure the relative permittivity, the cavity perturbation method was used. In this, the sample is inserted into the resonator and the relative permittivity is calculated from the changes in the resonance frequency and the quality factor of the resonator due to the sample. The equation 2 is used to calculate the dielectric constant, and the equation 3 is for the loss factor, where F1 and F2 is the frequency before and after the disturbance. Q1 and Q2 is the quality factor before and after the disturbance. UB is the volume of the sample, and UBC is that of the cavity. Parameters A and B are calculated from a reference sample whose permittivity is known. These are the steps. Sample preparation of B15 diesel biodiesel blend with palm oil at different concentrations. Later, measurement of the permittivity with the technique of cavity perturbation. Then, is there a relevant change in permittivity? No. So, and if yes, selecting model predictors and establishment of the determination model. Well, results. Applying different regression algorithms and considering only the dielectric constant, the lowest root mean square error of cross-validation was obtained by simple bridge last regressions, whose value was about 0.2% volume per volume, and the data were standardized. In the other case, in the case with only loss factor, considering simpler linear regression, the lowest root mean square error was of cross validation was 0.2%. 0.86% volume per volume. The feature was the loss factor and the data were standardized. So, conclusion, different concentration of palm oil in the B15, this biodiesel blend result in different dielectric constants and loss factor values at 2.45 gigahertz. The root mean square error of cross-validation of this model is lower than that of the model presented in literature. These results of this work could be used for the design of microwave microstrip cell aimed to measure of B15 diesel biodiesel blend by palm oil in real time and shape. These are the references, and thank you.
Thank you. Voy a quitarle el mute. Thank you very much, Eder Serafin. Do you have any question? Serafin, you told about you use different evaluation model, for example, cross-validation, support vector, regression. Which of these tools do you consider the most relevant or important in your results?
Yes, I use I was reading a lot of articles to select regressions algorithms, and they were the best regression algorithms for me, and for that reason I choose these algorithms.
For any particular reason?
Well, I use other algorithms, but the results were worst, and these were the algorithms whose results were the best. Yeah. For example, I use other neural network, for example, and was so good that only using, for example, simple linear regression had a better result than in this case, in my case, at least with my database, linear regression had a better result than neural network, for example.
Okay, thank you very much.
Thank you.
La tercera persona ya está conectada. Oficio. Mahali Hassan, can you hear us? Siguiente persona está conectada
Son los mismos.
en la misma.
Sí.
Que probablemente, como faltan 10 minutos para su presentación, probablemente no contestan. Faltan 7 minutos.
Tienen razón.
Doctora.
¿Sí?
Ok.
Le van a hablar a los carros.
The next presentation is a spectral characterization of the etal phase in epilepticization of temporal lobe using the wavelet transform. The PhD, Gabriela González. Bueno.
Thank you. Well, thank you, everyone. Thank you for this opportunity to present part of my postdoctoral research. This research is a multidisciplinary work between the Geophysics Institute at the UNAM, the bioelectric section at the CIMBESTAF, the School of Medicine, the Medicine of the UNAM, and the Faculty of Science of UNAM. Well, initially, I want to define epilepsy as a brain function chronic disorder clinically characterized by the presence of unprovoked seizure and a high risk of high recurrence. Epilepsy is considered the second most frequently diagnosed neurological disorder around the world. And in 2021, there were globally around 52 million people with this disorder. Physiologically, epilepsy is related to processes of hyperactivity and hypersynchronization resulting by an imbalance of excitatory and inhibitory neural circuits. In this case, the excitatory circuits with glutamatergic circuits are increased in comparison to the GABAergic or inhibitory neural circuits. Epileptic seizure can be focal when they start in a small region of the brain and they are localized only in this part, or generalized when they begin focally and then spread to both hemispheres. Temporal lobe epilepsy is the most common form for drug-resistant focal epilepsy. Around 25 to 35% of the people have this kind of epilepsy. And related to the drug-resistant epilepsy, is very important to consider this characteristic before 30% of the people around the world have this condition. The clinical diagnosis of epilepsy is mainly empirical and based on characteristics of symptoms, and the medical technique mainly used for this confirmation, classification on localization of the seizure is the surface electroencephalography. So EEG of this surface electroencephalography uses electrodes on the scalp and in order to recording the neuronal activity in real time. And they use this technique and as a specific localization of electrodes related to the 10-20% international system in order to map all the brain regions. Several graph elements are described in these EEG recorders and epileptic activity. Some examples are shown in the figure on the left, and from a slope wave related to delta waves, from to fast activity related to pulse spikes, frequencies around 30 hertz. The combination between the graph elements and the behavioral manifestation of the epilepsy helps to divide this abnormal activity in 4 phases: the ictal phase, pre-ictal, post-ictal, interictal phase. The interictal phase is the seizure per se, when the electroencephalographic and behavioral manifestation are prominent. Pre-ictal phase is the time before the seizure, and post-ictal phase is the time after the seizure, from some seconds to hours or days. The interictal phase is the time between between the ictal phases. Despite there are a very qualitative description about epilepsy, and this qualitative description are very useful in the clinic, currently there's no qualitative or quantitative consensus that objectively defines the onset of each phase, as there is no direct relationship between the electric manifestation in the behavioral manifestation in the seizures. For example, epileptic activity in EEG can be identified some seconds before behavioral manifestations. The ictal phase can be so short as 2 or 3 seconds. Seizures can occur with a behavioral component, for example, in the absent seizures, when we don't have a behavioral manifestation so prominent. Or a simple generalized spike associated with a myoclonic jerk can be considered a brief seizure. So we don't have a specific characterization of this activity. So in order to address this seizure, we offer another possibility to identify and limit this phase of electric brain activity using a quantitative spectrotemporal tool, in this case the Weber transform, in order to reduce this problem of subjectivity to characterize the epileptic phase. This spectral temporal tool could help with the determination of the onset and offset of each seizure. In this case, the most important phase is the ictal seizure because it's the seizure percent, and the identification, classification of the seizures, or even the localization specifically in focal epilepsy. We can localize the focus or the origin of the seizure. This idea was based on previous spectral information related to absence epilepsy, where a probable spectrotemporal pattern was observed when different wavelength model functions were evaluated. Using this kind of data, and we can see in the image time series of absence seizures related to graph elements called spike slow waves. And we can see when in this book of Rambo et al. 2015, they evaluate different wavelength model functions in order to find patterns in this kind of activity. And we can see the most important results, the first one, where we can see a specific pattern of frequency of the power frequency between 1 Hertz to and 4 Hertz. And these patterns were related to the onset and the offset of the seizure, specifically related to the graph elements in the time series. So to carry out our investigation or research, we use the data from 9 patients with drug-resistant epilepsy and temporal loss focal seizures with loss of consciousness. This data corresponds to 5 men and 4 women. 3 men had focal onset of the right hemisphere, 2 men and 4 women had focal onset of the left hemisphere. In total, we evaluate 21 seizures. All the requirements relating to the ethics committee were approved, and the protocols in the analysis protocol, in the data acquisition, and the diagnosis of the classification of the seizures were made according to the criteria for the International League Against Epilepsy. Each recorder were obtained using a video EEG system. The sample rate was 512 Hertz. All the patients remained in rest with closed eyes, and we used the information of 19 EEG channels based on the international 10-20% system. Okay, to carry out our investigation, we use 3 main processes. The first one was related to the extraction of the interface of all the recordings. The second one is related to the processing of wavelength reconstruction, and the last analysis were related with the analysis wavelength per se using the continuous wavelength transform. Related to the first extraction, all our recordings have the clinical onset and offset, and we use this information to short this period. Pre-processing with the inverse continuous wavelength transform was because this tool is useful to obtain information in a specific frequency range. In our case, we short information from 2 to 30 Hertz, and this step was useful to eliminate artifacts and hiding brain activity of interest. In this case, this activity between 2 and 30 hertz. Finally, the wavelength analysis with the continuous wavelength transport was used to find the spectrotemporal patterns. And in this case, was possible to use the inverse continuous wavelength transform because we use as a wavelength model function the complex model wavelength function, which was useful to obtain the complex part of the signal in order to reconstruct the signal. Okay. As a result, first of all, the duration of the ictal phases. In this case, we divide our data in 3 groups, men with focal onset of the right hemisphere, men with focal onset of the left hemisphere, and women with focal onset of the left hemisphere. In this case, we evaluate the duration of the seizure because, as we said before, that we can have very short seizures or very short ictal phases or very long ictal phases. So in this case, in all 3 groups, more or less, the duration of the seizures was around 1 minute, and no significant differences between the groups were found. And with this result, we could compare all our data. Results related with continuous wavelength spectra, and here I show 2 examples of spectrograms. In the upper panel, there are the time series, the original time series. In the middle are the spectrograms, and the left side there are the global wavelength spectra. So the most important result was that we found 2 patterns. The first one was related with a hypersynchronization in around the theta band between 2 and 4 hertz, and then we found a big dispersion of frequency dispersion between 2 and 30 hertz. And these examples were the channels related to the channels nearest to the focus. In this case, was a man with focal onset in the right hemisphere. So these examples are this example represents the temporal channel T4 and T6. So in order to observe if this pattern was observed in another channels, we create these images where we compared the right hemisphere, the line in the interhemispheric line, and the left hemisphere. And we can see in this case, when the man had the focal onset in the right hemisphere, that we can see the hypersynchronization and the dispersion between 2 and 30 hertz more prominent in this hemisphere in comparison to the interhemispheric line and the another hemisphere, the left hemisphere. So in this representation, we can or we could observe also another pattern was this mark in delta activity. So we can characterize this kind of epilepsy with 3 patterns: the delta information before to the hypersynchronization in theta band, and then the dispersion in between 2 and 30 hertz. In a more specific or more detailed study in this related to this hypersynchronization, we could identify 2 patterns or 2 types of hypersynchronization: the discontinuous form and the continuous forms. The discontinuous forms is related to a stop of abnormal activity between the hypersynchronization in the posterior dispersion between 2 and 30 hertz, and the continuous hypersynchronization were related with this hypersynchronization between or inside the dispersion from 2 to 30 hertz. So we can have these both types or activity, but in the most important thing that is that we can observe the hypersynchronization in the posterior dispersion. in order to compare the values, the frequency values between the channels nearest to the focus and the other channels, we create these heat maps in order to understand what happened with the frequencies. Related to the groups, we can identify that hypersynchronization have frequencies in delta and theta bands, and delta band is more or less the same frequencies or range in the same frequencies in the three groups. But in the case of the activity in theta band, we can identify that in the people with focal onset of the left hemisphere, the frequencies are higher in comparison with the right hemisphere. And finally, we could understand what happened with the power dispersion around on the scalp, around the brain. And we can, and for each patient and for each seizure, we create these heat maps in order to identify what happened with different frequencies on the brain. And we can see that, for example, high frequencies like alpha and beta bands are more near to the focus of the seizure, but related to delta and theta bands, we can see that this information is dispersed in the total or in the most parts of the brain. And in the case on this range between 2 and 30 hertz, we can see that the delta and theta bands are more, they have more contribution to the dispersion of the seizure. And in conclusion, an spectral pattern was identified in the ictal phase from patients. In this case, was the 75% diagnosis with temporal lobe epilepsy using a Fourier transform. This pattern includes 3 phases: the delta phase, the hypersynchronization in theta bands, and the dispersion of the activity between 2 and 30 hertz. This pattern was irrespective of onset, lateralization, and sex. So it's the same for all the cases. And the onset and offset of these seizures in temporal lobe will be restricted to this pattern. So we can, we could make a match between the start of the seizure with the pattern and the onset of the seizure, the onset of the seizure. And finally, relating to the power of frequency dispersion head mass, this information we didn't find a specific patterns because we consider that this dispersion was more related to the damage in individual person, because if we have a specific type of seizure, we can have different damaging of the brain depends of the people. So it's individually. So as a future work, we need additional data to confirm the robustness of this method. For example, EEG data from women with focal onset of the right hemisphere, because we only use women with focal onset of the left hemisphere, the evaluation of effects of pharmacological treatments, and the correlation with the qualitative observed graph elements, because in this case it's very complicated understand which kind of graph elements having this kind of seizure, because it's not so easy to identify them, and the spectral patterns and the alignment of these patterns with the behavioral components, because in this case we only have the information of the electroencephalographic recordings, but no had the information of the behavioral component. So it's very important in order to classify epilepsies. And thank you. Thanks.
As I'm curious, I'm not of that field, so sorry if the question is too obvious. How difficult is to acquire those signals? Do you have to wait until they have an epileptic attack? Because you said that you have them with the closed eyes.
Mm-hmm.
So I would like to know how, because you need more data. So how difficult is to acquire that new data?
In this case, I use data from database.
Okay.
Yes, I not obtain directly the data because it's very complicated. But in this case, one of the most important things is that clinically you can identify the onset and the onset of the seizure. And when the seizure appears, the clinics can identify and mark the times, and we use these times in order to say that the digital phase starts and ends in this part.
Okay.
Yes, but it's very complicated. For example, in the case of absent seizures, in these cases, there are not behavioral components, so it's easier to obtain the data or cleaner data. But in the case where the people have this manifestation of convulsion of this kind of activity, myoclonic activity is very complicated because of the information of the muscles impairs with the EEG.
Okay.
Yes,
Thank
very
you.
complicated.
Thank you.
Doctor, these are very interesting and complete research. Congratulations. How do you validate this result conclusion?
In this case, for example, in many qualitative descriptions, there are specific frequencies that the clinicians or the doctors identify these frequencies. For example, the slow frequencies or fast frequencies. So in this case, we try to do a match between this qualitative characterization and quantitative characterization. For example, in some cases say they say that for example the epileptic activity is only in the delta band, no, for example, and we can identify, for example, is the delta band is, for example, between 2 and 4 hertz. But for example, we can identify that the activity is between 2 and 5 or 4.5 hertz, and not exactly between 2 and 4 hertz. So we try to propose quantitative mechanisms in order to identify characterize the seizures. So it's very complicated, and in this case, the manifestations are a very good component, a very important component in order that the clinicians say that the seizure starts here. But in our case, it's complicated because we don't can identify, or we cannot identify the behavioral component. Yeah.
Thank you very much.
Yeah, I have a question. In the EEG procedure, is there an standardized sample rate? Because you mentioned about 512, and I think that is too fast when you are looking for frequencies that are below 10 hertz.
Yes, sometimes, for example, this sample rate is related to the standard in the clinic. For example, and in research we use, for example, 2028, for example, or higher. But in the standard in the clinic, there are 188 or 521.
Do you consider it is important to make conclusions?
Depends, for example, the frequency that you are looking for. So, for example, if you are looking for high frequencies, it's necessary as a sampling rate higher.
Yeah.
But if you looking for slow frequencies, you can use a normal sample rates about 128 hertz. Yes, it depends. Question? Yeah.
Muchas gracias.
No llegaron a preguntarles. Entonces no ayudaron. Bueno, no sé.
Biomedical, are you ready? Good answer.
Sí.
Good answers.
Sí.
Biomedical, can you share with us?
Gracias, Iván. Sí, porque de hecho la persona que va a ir a ver, ¿no? Por
Antes was the reunión.
¿Sí?
Está grabando, ¿no?
Sí, pero...
Sí, sí. Ya se envió.
No respondo. Ok. Adriana Paola.
Me siento yo.
Okay. The next presentation is modeling and experimental validation of biomedical of actuador based on octopus vulgaris.
Karina Gutiérrez.
Karina Gutierrez, go ahead, please.
Thank you. Hello, good afternoon to everyone present in this room and the online room. Our project is modeling and experimental validation of a biomimetics of actuator based on octopus vulgaris. The authors is Adriana Arias, Karina Gutierrez, and the Dr. Álvaro Anzueto and the Dr. Adrián Ramírez. I give you an introduction about what is our project and the logic that we use about the project and the results and conclusions that we obtain in this project. This project presents a systematic design about robotics and is inspired in the pencil motion about the octopus vulgaris tentacle. And we combine the robotic and the inspired in the biological functions in the octopus vulgaris tentacle. The sub-robotics is an emerging field in robotics because it's compared to the traditional robotics and the rigid robotics. This area in focus with materials that it's that combine the flexibility and the nomadic actuation. But in these cases, we use flexibility and comparability materials. We use the octopus vulgaris because it's an organism with a unique anatomy. Why? Because it has a good facility to adaptive to the form of different objects and has the in natural ambient of this animal. These have a facility to navigate it in high spaces. To first our project, we made an experimental test with octopus vulgaris in post-mortem medium. We made this proof where we introduced these tentacles in a medium with increment temperature water. To first, we obtained the relaxing of complaint structure of this tentacle, and then we obtained a simulation of the prehensile movement that the octopus vulgaris made for the subject of the objects. And finally, we obtain these angles. And can we see the angle in the most distal of the tentacle
we obtain a angle close to 89.2 grades. That is smaller than the angle that we obtain in the base of Vulgaris body, that is 104.7 grades. And next, we focus in this animal. Why? Because the flexibility to navigate and adapt to different spaces have different strategies to do a new area in robotics. And his muscular rostret is able to take different objects and the biomimicry, because we inspired in biological functions about the octopus vulgaris tentacle for a new system robotic. We use this silicon for create the soft actuator. And in this case, we use the EcoFlex 00 silicone. And in this case, this consists in a part A and part B. And the part A is the catalyst, and the part B is the part A is the polymerase, and the part B is the catalyst. And in this case, we obtain a ideal silicone to our project. We use the geohyperlastic model for helps to understand the idea that we need to understand the elonga to the tentacle, and next back to the real model without breaking the silicone. Our first model was with a single camber. In this case, we use a rectangle prints model with an internal camber, and we introduce pressure in 12 PSA. And as you can see, we obtain a movement, but in the external part, we have information of the material. And in this case, in this case, we put a correlative flat to limit this information in the external part. As you can see, in this case, are healthy, but not is a good result that we expect. In this case, we change our model to a multi-camber internal, and we put them cambers internal in the same rectangle prints. But in this case, we separate, we put a little space between these cambers to have a better result. And if you can see, the angles that we obtain, it's close to can we hold an object. But finally, we can take the last idea and change the model for a triangle model with multi-chambers internal. In this case, we use the same internal pressure with 12 PSA. And if you can see in the simulation, we obtain a final angle close to the experimental test that we do in the beginning project. And finally, we have this table with the comparison of being angles among tentacle models. In the first, we have the angle obtained with the thermal simulation. obtained 76.7 grades with the first model that is single camber with EcoFlow 00 theory. In the condition of 12 PSA, we obtained 135.3 grades. In this model, simulated in ANSYS, we obtained an angle closer to the physics model that we made, and we obtained 134.8 grades. In the second model that we made, we obtained 112.8 grades. And in this same model, simulated in ANSYS, we obtained 112.6 grades. The final model was well not realized in physics, but in our simulated in ANSYS, we obtained 98.9 grades. As you can see, the angle that we obtained in this simulated in ANSYS is close to the angles that we obtained in the first experimental test with the postmortem octopus vulgaris organism. In conclusions, we in each models we obtain a conclusion different to the last model triangle multi-chamber. In our future work is the fabrication and experimental test of the multi-chamber triangle prototype that we simulated in ANSYS. These are some of reference that we use for our project, and thanks for all. And any questions?
Okay. Okay, no.
No, 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 no.
Okay.
No.
I would like to know what are their future works, because this is quite interesting. I've never seen this before. So just as a matter of curiosity, what is your future works with this?
Yes, our future works is for our titulation in the university, but have a good point, because the future work of this model is that this project can hold objects, and in our case, we have the specific meditions, the specific,
Yeah.
yeah, and in our case, it's with ceramic cup, and in this model, the length of this tentacle is close to 32 centimeters approx.
But sorry, but the idea, the principal idea is mimetize the octopus with this project.
Yes.
This is the principal idea.
Mhm.
And now for this titulation. Great.
In a good point in this case is because in a natural habit in the of the octopus vulgaris, these have this can be a good complex movements and with delicate objects. And where we use a ceramic cup, it's a delicate object that don't need rigid components for don't break the pieces or something like that.
Nice. Thank you.
There are any question more?
Thank you. Linda, ¿qué se hace en estas situaciones?
Pues no se presentan, no contestan, entonces. Gracias.
Ah, mira, ahí está, I am Mohammed.
Ok. Le voy a hablar, puede. Mahadi Hassan, are you ready?
Yes, I'm Muhammad Rizwan. I will be presenting paper ID 134 and
The
140.
next presentation is EOT based hemoglobin level detection system for anemia patients. Imagen processing. Mahad Hassan. Hassan.
Okay, should I start? Can you see my screen? Excuse me, am I audible? I'm sorry, I'm not getting you. Am I audible or no?
We can hear you.
Okay, then let's start.
We can
Hi,
see
this
and we
is
can hear you. Go ahead, please.
okay. I think you can see my screen too. So this is Muhammad Rizwanuddin, and I'm going to present IoT-based hemoglobin level detection systems for anemia patients with image processing. So it was an idea paper, and we have boiled it through. Let's start with the presentations. So let's start with the basics. As you can see, the outline of the presentation will be we'll cover some introductory part and then literature review. After that, we'll go for the design simulations that we have built, and then the analysis part will show you some results that we have covered. So in introductory part, we must like to add that we has been working on IT-based device that we want to integrate on physical demonstrations like hemoglobin detections or any kind of anemia patient detection systems. So what we have developed, it's just an image that can detect whether patients or human are having leakage of hemoglobin or not. So let's start with this part. The purpose of our experiment or project was very simple, to detect the colors of nail or to detect colors of eye. So we started from the detections, anemia detections from the nail colors. You can see the image over there. So from here, we can identify whether we should get at a clear image by using nail or clear image by using eyes. So starting from there, you can see that we have demonstrated through 4 different color combinations. If you get a reddish color, that means you have no issues with hemoglobin. If you have more whitening color, then it can be said that you are facing some issues like that. And the motivation was to implement these things for daily use patients. Like it is very tough for our country to go to the hospital and identify whether he is having a hemoglobin deficiency or not. Rather than that, if you can have assistance that can detect your hemoglobin deficiency in home, it will be easier for the patients in our country. So you can see most of the doctors try to find out whether he is facing hemoglobin deficiency from the eyes as well as from the nail or from the tongue. So from eye, you can see if you have a hemoglobin deficiency, it will become somewhat like less reddish. But if you have a good sign of good hemoglobin, then it will be what we say reddish. So what is our motivation? To build a simple systems that can identify these kind of things. So what we did later, we built a system that should be used ESP32. It's a very basic camps as we are just started the things that we thought of. So we just use ESP cam and a processor that is known as ESP8266 that can process the image throughout the systems. So ESP32 cam will detect the image from any patients or any human, then it will pass through the what we say a microcontroller processing unit that will identify the discrepancy of colors. I mean, discrete colors that what colors does the image consider or have. Then it will extract the features and it will levelize the hemoglobin level. From that, we can classify whether we have a normal hemoglobin levels or it is a critical one. So it can display in LCD or LED display as well as it can send it to an IoT floor. We can use Blink or things like that. So the methodology that we have already discussed, the flowchart will be something like it will take the image, then it will process the image to identify hemoglobin deficiencies. And from the images, it can classify types of hemoglobin levels and whether it is critical one or a normal one, and can display as well as send back the data to the Internet of Things through Blink app or Things app, whatever you can use. So after building the hardware or for hardware development, detection systems was built something like that. We can put an image over there. We started taking the image of people as well as some fruits. So we try to identify whether our systems can detect colors or not. For that, we build the systems and identify the images through normal images of human as well as fruits. As the simulation was successfully done, we have built the hardware. The hardware consists of a camera module, you can see over there, and a microcontroller unit that is ESP8266 or NeoMCO, that consists of a display unit. So these things can identify and detect hemoglobin deficiency. So the basic simulations as well as circuitries was to identify, to detect the image, to classify it, and the levels can be displayed in LCD display by using I2C, and as well as we can send back this to the cloud server. That was very basic things that we have built, and we are the initial stage. We are on the initial stage to build the systems, and we successfully build this, but the packaging as well as the proper systems is still due, still working on these hardware. So the hardware we used microcontroller ESP32 microcontroller as well as ESP32 cam and a display with power bank module with some uh, control unit. So from that, we have built a hardware that primarily that can detect the image and it send back to the site that we have developed for IoT devices. After building the systems, we have demonstrated the systems for real field implementation, and we find out some hemoglobin level detections. You can see over there, and if you have a lower hemoglobin that is range of 4 to 8, that is deficiency, and if it is higher than 10 or 14 gram per deciliter, then it is normal range. So we try to use RGB as well as some lights to identify these good images, and hemoglobin level can be detected by these systems. So from the analyses as we have got, we have put the means value in x-axis as well as the differences in y-axis. You can see that the regression line derived from the data provides clear trends that whether we get normal people or a deficiency in hemoglobin. We can see that most of the people has mean value or average normal value, and some of them are suffering from anemia, or it can be an anemia for the test. So the thing is, the system that we have built, it can detect the hemoglobin deficiency by using just an image rather than invasive systems that require blood. So the primary result and the analysis shows a good performance that we have built. You can see the hardware. It's just packed inside module, but we are on to develop these systems as the professional one if it is working fine, and we'll go for more complex hardware and PCB design after these things. If it is working fine, we will go for the good resolutions of camera module. Then I think we'll have a better primary investigations on hemoglobin levels. So from the systems we have, as we said, we have already a non-invasive systems that can timely detect hemoglobin. So it can be used for regular investigations of an anemia patients or any patients that is suffering from hemoglobin or any kind of blood deficiencies. And the cost of this system is very low, and it will help the healthcare systems in a great extensions, we believe. So what we are trying to prove that we just got an idea that we will try to implement hemoglobin deficiency detection systems by using just an image processing. And we have successfully built that. And in future, we will try to build AI-based systems that will have some previously trained data, and will train the systems to identify whether whether the data is more accurate or not. For that, we need previously recorded data, and we are working on that. So this is the concluded line. We have already implemented the systems, build the systems, and identify the hemoglobin deficiencies as well as normal ranges of the hemoglobin. And in future, as I said, we are trying to integrate these IoT-based systems in large extents, as we are also trying to build an app that will be working functional on smart devices, and that can detect and then can suspend or detect or analyze the anemia patients for instant. That will be very helpful for what we say for the medical systems. Those are the some references that we have used. I'm done with my presentations. Thank you. Now the floor is open for questions. Do you have any questions regarding this?
Any question?
Mahadika-san, I have a question. You
Okay.
are using regression model. Do you have considered another model?
We have considered a model for image processing. It's just MATLAB code that just detect the initial image of a reddish, a red signals. Just the system is compare the image that we have. Just that's it. It's just an initial model that we have used.
Thank you. Any question more? Okay. Thank you, Mohammed. The next presentation is with Mohammed. The name of the presentation is Fault Detection System for Session Fashion. Go ahead, please.
Okay. Though this works is been done by a team, I was also the part of the team. I'm presenting the fault detection systems again. Just give me a minute. I think you can see my screen.
Yes, we can see.
Okay, so let's start with this one. We have many authors in this page. So it was a basic paper like the previous one. So what we did actually, we had some ideas to implement and we try to build in primary systems. And if it is working fine, then we are trying to build up the systems for regular patients. So this is also built for people that is suffering from seizure or elderly people that we can detect whether he is in good positions or not. For that, we have built the systems. So the systems mainly the presentation mainly outlined as some reviews from the literature and the methodology that we have used, and then we build the primary hardware that have been working fine, and some results that we have got so far from our systems. So from the starting, we can see that these systems, it's mainly aimed to detect fall or abnormal activities or any of any elderly patient and of any seizure patients that we can identify. So from that, we can see that we can use an IoT device like NodeMCU or ESP8266 to remotely monitor and control, and MPU 6050 and NEO-based GPS systems to identify the fall detections. So from the introductions, what we have started ready to detect the seizure disorders, they might have an uncontrolled fall, and we can see that for that we can use a cloud server that can detect any falls and then can identify or send the data to the doctors as well as the family members that who are really aware of the elderly people or the system. So we have already studied many related works. So the literature review was EMG based or ECG based systems that being used in belt or raised or in watch. But the cost of those systems was very high, and though we have a good precise detection systems, but still the systems considering the developing country, it's very high. So the gaps, it's the cost as well as simple systems. We try to figure out the solutions for that, and we build and seizure detection systems that we are going to discuss right now. So the objective was to develop a simple and reliable system by using just node MCUs and some sort of gyroscope sensors, and that can be detected by the sensors and can send back these data through GPS or IoT systems. And the performance, it's also been detected and primarily identified that whether the systems is working fine or not. So to build the systems, we have used Node MCU, gyroscope sensors, new module, some power bank or battery module to power up the systems. In total, the systems component was around 25 USDs. So let's start with the system architecture. So what we have built, it's just a motion sensor and a microcontroller device that can detect the systems, and a Wi-Fi module or GPS module that can send the data to the monitor of seizure patients or in the medical systems. That ensures caregiver notification within seconds of all the detections. So this is the basic hardware schematics that we have. We have the GCM systems as well as the MPU systems for our instant fall detections, and in the node MCU module that has been powered up by a buck converter from the battery module. So that was just simple systems, but the combinations or the prototype development was quite difficult. And as we are primarily using the discrete systems or discrete module, the system it's quite gave us quite simple result, but we are trying to figure out whether we can build this whole systems together to provide a good systems. So this is the primary hardware of our systems that is being developed, and in board, we just use wires and connectors to identify simple changes in directions or fall of the circuits. So what we were planning to implement these systems in race bell or in what we say in bracelet by modifying the systems in simpler way that can detect and a fall of or a sudden changes of any directions of any patients who will be using this valve. So basically, we have used Blink IoT platform to detect these things. As it is free software, we can easily detect the changes in any sensors or any information that is being provided from NodeMCU. The Blink platform was developed according to the seizure patients, online and offline, and customized dashboard that you can see over there. We have built these things too. The Blink app can be used in laptop and any computing system as well as in mobile phone that can identify the sudden changes or fall of any patients from the system that is providing. And by using Blink, we can identify weekly data or monthly data of the patients, whether the seizure condition is stable or unstable, what was the frequency of fall or sudden changes of his movement. We can detect all those things and record these in Blink. So this is the basic codes that we have provided, and from that we find out that our systems, as we have identified, it is almost 80% efficient, and we are trying to modify these systems that can be that can detect any systems, any kind of fall in instance that make it to 90 to above 92% efficiency. So as these are very basic systems that can detect a fall and it can notify us accordingly. So there is no specific performance drop or anything else, but we are implementing these in a medical hospital for various patients. We have already built 10 of these systems, and we are identifying that whether the system is good for patients or it is bad for getting an extra belt or raised belt for the patients. But the response that we are getting is very good so far. So from the systems that we have built, we have sub-comparative studies that we used in other systems that is already built. You can see that the system that we have showing there, they're using 3-axis accelerometer and gyroscopes, and they're using expensive Raspberry Pi that cost almost more than $120. And the systems use smartwatch built-in motion sensor. These are the very basic systems, and built-in systems can be used for that. But for the watch, the cost is very high, around $200. And another one just used Arduino Nano and GSM module. It costs almost $95. Whether we just use the 3-axis accelerometer MPU 6050 that can do the same things, but the system cost is around $35. So the as I said before, we tried two things, that the cost should be minimized and the system should be as simpler as possible. We are working on the combined systems that can be built in a bell and any variable patch that will be simpler. And according to the cost that we are showing, it is very very user friendly and feasible to use in any seizure patients in a developing country like us. So from the comparative study, we can see that we have built a successful systems, but still, as we are using basic components, we have to use the sensor as well as the components in our professional extent. So some challenges we have faced, that the sensor that provided the data has many noises, and the GPS signals sometimes lost in certain places, And if in fact we are using IoT by using Wi-Fi, and our country in every place Wi-Fi is not available. So we are trying to fix these things out, and these are the basic steps that we are trying to modify as we are facing some challenges there. So the improvements is to apply machine learning or AI module in these systems that can detect the fall types from basic data that will be provided, and a Bluetooth or RFID indoor localization system. Just say the patient is in room and we are staying in another room that can be controlled by Bluetooth or RFID module. And as I said, we are trying to build a compact wearable systems and a customized cloud dashboard, replacing Bling limitation as we are using free software to do that. So those improvements are ongoing. We are working on that. And from that, we believe that we have some better scopes in future that will integrate telemedicine systems and the systems that's as we can what we say as Caesar patients in online. If we can put him in online, we can detect many things from him, from fall detection to ECG signal, as well as remote hospitalized control and monitoring systems that will give us a feasible solutions with minimal cost that will be commercially scalable for lower income countries like us. So this is the concludatory part. We have built the fall detection systems, and it was working fine, though we used very basic components, and the improvements is already going on. We hope within a short period of time, we can build professional systems rather than using all the student-based components. And we are already going for ICD RBD contact that will provide us the proper amount of money to build the systems that will be more professional and scalable. So those are the references that we have used to develop these systems. And done with this presentation, as it is a very basic systems. I think we can build these systems in short amount of time. So that's it. I'm done with this. Now, do you have any questions? Thank you.
Question?
I have a question. Can you explain me what did you reset time? Because
Response
I
time?
don't see what did you do, the velocity of your implementation.
Oh, we didn't add any time for that, but the response time is 2 seconds.
And the current consume, because it's small, but it's necessary to check with the battery the time.
Yes, we have used a battery. Are you talking about the hardware? This is the battery module that we have used. And it can respond very well. We can detect the systems within 2 seconds, whether it's a normal fall or it's a sudden fall.
Necessary that you improve your reset time. It is necessary that you improve your reset time or not?
Oh, no, we didn't improve our present times at all. We are working on that.
Any question more? No? Okay. Thank you.
Thank you, sir.
Okay. Thanks a lot for sharing your time, your research, and your knowledge. This session is finished. Thank you.
Thank you.
Thank you.
Thank you.